Hello everyone, Victor is here, and in this video let's talk about the resonance structures. So from general chemistry you probably remember some conversations about resonance for different ions, like let's say if I were to draw CO3 2- and I needed to show the Lewis structure for that, there are several different ways how I can show this Lewis structure. So for instance, I can show my Lewis structure like this, or like that, or like this. All of these three structures, they are what we call resonance contributors, and we signify the relationship between those by showing the double-headed arrow like this. And the reason why we say that these are contributors and not different structures is simply because all these three structures, they represent exactly the same species. Important thing to keep in mind here: resonance structures, they're not different molecules, they're exactly the same molecule, however there are different representations of this molecule. Drawing resonance contributors like this allows us to easily keep track of the electrons in the molecule, where the exactly electrons are, where the lack of electron density might be, or where the excess of electron density, like in this case, and what sort of bonds we have in our molecule, whether those are single, double, or maybe triple bonds. Importantly though, the contributors that we have for our resonance over here, they do not describe the molecule adequately. Those are merely simplifications. In order to truly describe the nature of this molecule, we need to draw a resonance hybrid structure, which is essentially going to be a superimposition of all of our structures together, making kind of like an average between all of those. And the resonance hybrid for my particular molecule would look like this. Now, it's really difficult to work with hybrids because what exactly is this delta minus? Well, I can physically calculate my delta minus being we have the full -2 charge, which is going to be distributed over 3 atoms in my molecule, so my overall delta minus is -2/3. But what exactly does that mean? It's sort of like a partial charge. What exactly am I going to be doing with that? Where exactly are my electrons? Do I have a single bond, or is it a double bond, or what is that, 1.5 bond that I have over here? That stuff is confusing. Not to mention that whenever we are trying to draw the mechanisms of reactions, or we are simply trying to have a good bookkeeping for everything that we have in our molecule, it's exceptionally difficult to work with resonance hybrids. So we pretty much never do, and we're always going to use resonance contributors to describe our molecule. Yes, as I've mentioned, it does not describe our molecule adequately, but it describes it well enough for our purposes, so we can still predict the reactivity of the molecule, and we can predict bond orders that we have there as well. But before we go into the discussion of the resonance in organic molecules, let's talk about one other important aspect of resonance and reactions in organic chemistry in general that we are going to use quite extensively, and that is curved arrows. Curved arrows, or sometimes they're also called curly arrows, is a tool that we are going to be using to describe the movement of electrons or movement of electron density in general. So whenever we are showing a curved arrow, we're going to show it from the source of the electron density, and that source can be either an electron pair or it can be a bond, which essentially is an electron pair as well. And these electrons are going to be going towards the electron sink, which is going to be some sort of acceptor of said electron density. And the electron sink can be either atom, or it can be kind of like a space between the atoms where the new bond is going to be formed. So to give you an example, let's go back to our resonance structures for the CO3 2- anion that I have for the carbonate anion, and see how we can use the curved arrows in that case. I have a resonance structure or resonance contributor where I have my electron pairs around oxygen as such, and if I want to go to the second resonance contributor where I have electron pairs around my oxygen distributed in a different way, then in order to do so, I'm going to take electrons from one oxygen and push it towards the other one. Of course, I'm going to show my negative charges over here because we want to make sure that we are not missing any charges, because as I've mentioned before, charges are not implicit. So what I am noticing here is that I had electron density over here between my carbon and oxygen. Now, the oxygen that I have up above has an extra electron pair, which means that the electrons from the pi bond must have traveled onto this oxygen and became that electron pair. I am also seeing that the electron pair that I had on the oxygen on the left now became a double bond. So in order to accomplish that, I'm going to take those electrons and I'm going to move them between oxygen and carbon. So this way, the pink electrons become the pink double bond, while the green electrons from being the green bond became the electron pair on the oxygen. This way we can show exactly where electrons used to be, where electrons went, and we are not losing any electrons in the way while we are doing this type of a transformation. The curved arrows can be used for both resonance and reactions in organic molecules as well, but for right now, since we are using the curved arrows for resonance, that's what I'm going to stick to, so I'm not going to talk exactly how we are dealing with curved arrows in the case of reactions. That will be a conversation for a different day. So when it comes to the resonance, there are four most common types of resonance structures or resonance interactions, if you like, that you are going to see. The first one is going to be an interaction where we have an empty orbital plus an electron pair on the nearby atom. So remember how in the hybridization tutorial I was talking about empty orbitals? So that is one of those cases. So let's say I have a carbon over here with a positive charge which is going to represent an empty orbital. And next to that carbon I have, for instance, an oxygen. And oxygen has a couple of electron pairs. Now what can happen in this case is that my oxygen is going to donate its electron pair in between carbon and oxygen, making a pi bond, and in this case we're going to have a resonance contributor that looks like this. I still have my carbon, now there is a double bond between the carbon and oxygen. I still have my oxygen with only one electron pair left, and now oxygen has a formal positive charge. If we wanted to double check the formal charge on the oxygen, we know how to do it. It's going to be valence electrons minus lines minus dots. So in this particular case, valence electrons for the oxygen is going to be 6. If we find its position in the periodic table, we know that oxygen is sitting in the 6th group. That's why we have 6 valence electrons. It currently has 3 lines connecting it to things, and we have 2 electrons around that oxygen, so that gives me an overall charge of +1, just like that. A resonance like that does not have to be with carbon and oxygen, of course. We can have a whole bunch of different structures, for as long as you have an empty orbital and an element next to that empty orbital has an electron pair, typically we're going to be able to perform this type of resonance. So another example will be, let's say I have boron, and boron, if we look at the periodic table, only has 3 electrons, so naturally boron has an empty orbital when it bonds to other molecules. And next to this boron, let's say I have a nitrogen atom with an electron pair. So in this case, nitrogen can give the electron pair towards the boron, can share those electrons with boron, and what we are going to end up with is a species where now I have a double bond between my boron and nitrogen. Nitrogen will have 4 bonds, and we are going to have now formal positive charge on the nitrogen and formal negative charge on the boron, like that. In the first case, where I had carbon and oxygen, I had the overall +1 charge on my molecule to begin with, and I ended up with the overall +1 charge on the molecule as well. In the second case, my molecule was neutral to begin with, there was no charge on that, and I ended up with a neutral molecule as well, because I created a plus and a minus, so overall those two charges have cancelled each other out, which means that I didn't create any extra electron density, I didn't destroy any electrons, the overall electron balance within my molecule stayed just as is. So if I wanted to use an example where I draw my resonance with bond line structures, let's say I have something like this. I have a sulfur in a 6-membered ring right next to a carbocation over here. I remember that based on my bonding patterns, sulfur needs to have 2 electron pairs in order to be neutral. So in this case, I can do a resonance between this sulfur and a carbocation, which will give me the next structure that's going to look like this. In this case, sulfur will only have 1 more electron pair left, which means that we are going to end up with a formal positive charge on the sulfur. So like in previous cases, this molecule had an overall plus charge, we still have an overall plus charge as well, so I didn't lose any of my electrons. Remember that when we are dealing with the bond line structures, like the last example that I have here on the screen, the electron pairs, they can be implicit, we don't have to show them. So always remember that although they may not be shown, they are still there. So don't just forget about their existence, because otherwise you can easily forget about the resonance structures that you might have. And as I've mentioned before, resonance is a huge tool in organic chemistry, so if you are missing resonance structures or you are missing resonance stabilization, then potentially you are going to be missing out on the important bits of information from your molecule. So always be very vigilant about those pesky electron pairs that can be hiding on your molecule. The next common pattern that you are going to be seeing when dealing with resonance is going to be a case where you have an empty orbital and a pi bond nearby. So if I again start with empty orbital on the carbon over here like a carbocation, and nearby I have a pi bond, then in this case what I can do, I can take the electrons from the pi bond and I can move them towards my carbocation. Now if I number my atoms as 1, 2, and 3, so what essentially I'm doing in this type of resonance, I'm taking a pair of electrons in between carbons 2 and 3, and I am placing those electrons between carbons 1 and 2. So in this case, I'm going to now end up with a double bond between carbons 1 and 2, so the double bond is right over here. The rest of the bonds are still there, but carbon number 3, now that one does not have the electron density around it to complete the octet, so my formal plus charge is going to be on my carbon number 3. When it comes to drawing that in the bond line structures, we're going to see a situation like this. Let's say I have a double bond over here, plus over there like that. I'm going to take the electrons from the pi bond, move that towards my carbocation, and I'm going to end up with the next resonance contributor where my plus is now on the right side. So if I again number my carbons as carbons 1, 2, and 3, I have taken electron density between carbons 2 and 3, I've placed that electron density between carbons 1 and 2, and carbon number 3 does not have electron density around it anymore, so because of that it's going to have a plus charge. The next common type is going to be when you have an electron pair on some sort of element like nitrogen, oxygen, or something else next to a pi bond. So let's say I have a situation where I have a nitrogen atom with an electron pair, and that nitrogen is sitting next to a double bond like this. What I can do in this case, I can actually start with the electron pair, I can push that electron pair towards my carbon-carbon double bond, but now we have a little bit of a problem. This carbon in the middle over here right now currently has 1, 2, 3, 4 bonds, which means that that carbon has a full octet around it. It cannot accept any more electrons, so the only way the middle carbon will be able to accept electrons if it pushes some electron density away from itself to its neighbor. So in this case, what I'm going to end up with is going to be a structure in which I do have a carbon-nitrogen double bond, but my carbon on the right side now has the electron pair which used to be a pi bond, but now it's just an electron pair on carbon. On top of that, because nitrogen has shared its electron density, I'm going to have a formal plus on the nitrogen like that. So I had electrons on the nitrogen shared between nitrogen and carbon number 1, and now nitrogen and carbon number 1 has a double bond, and carbon number 2 will have an excess of the electron density on itself. It will have this electron pair, so because of that it will have a negative charge. In the bond line form, I will see something like this. Let's say I have a molecule that looks like that. I'm going to start by taking the electrons from the nitrogen and pushing them towards the double bond. Since in this case it's exactly the same situation, this carbon cannot accept more electrons due to the full octet, because I will remind you that we do have an implicit hydrogen over here. We'll have to take our double bond and we will push those electrons towards the nearby carbon, and that will give me the resonance contributor that looks like this. I have a nitrogen with a double bond, then I have a nearby carbon with a negative charge, and nitrogen of course is positive, and then I have the rest of my molecule. Finally, the last type of a resonance that you are going to see on a somewhat regular basis is going to be when we have a couple of pi bonds next to each other interacting with each other. So in this case, let's say I have a carbon-carbon pi bond over here, which is next to another carbon-carbon pi bond like that. Well, here, in order to create resonance, I would have to polarize one of those bonds by pushing electrons towards another double bond. Here we are going to have the same problem as in the previous case, where my carbon number, what is it going to be, number 3 over here, this carbon, will not be able to simply accept that electron density, so because of that we'll have to take the electrons from the pi bond on the right side and push it to the nearby carbon. Now, what I'm going to end up with is the resonance where I have a double bond in between my middle carbons. Then carbon on the right side has an electron pair, carbon on the left side hasn't gotten any electron density, so we're going to have a positive charge there, and we're going to have a negative charge on my carbon on the right. This way, the molecule was completely neutral to begin with, and it is still neutral, although it is very polarized. The resonance like that is not the most common type of a resonance that you are going to be using for your analysis. However, you are going to see that from time to time, so it is also something that you gotta keep in mind. Using my bond line structures, I can show this resonance as following. I'm going to draw a molecule, and let's say I'm going to polarize it to the right as well, like what I did in my example above. Now, what I'm going to end up with is the double bond in between the middle carbons, electron pair on the carbon on the right, so the left carbon, the outmost left carbon in the structure is going to have a positive charge. The outmost carbon on the right is going to have a negative charge, and overall my molecule is neutral. Remember, the most important thing during the resonance is keep a very keen eye on your charges and the overall balance of your electron density. You should never have a molecule that used to be neutral and then accidentally became, positively charged, or was neutral and then became negative, or was negative and then became positive, or whatever else might be the case. If your molecule had a charge, the overall charge, we need to keep the same overall charge, because I will remind you that the resonance only shows you different contributions of different styles of structures that we have, but overall all resonance contributors represent exactly the same molecule, which means that I cannot have the same molecule with, different overall charge. I cannot have molecule A being negatively charged and positively charged overall at the same time. That just wouldn't make any sense. So always keep an eye on your charges when you are dealing with resonance. Let's look at a couple of examples. In the first molecule, I have a couple of pi bonds and a plus charge. I remember that plus charge represents the empty orbital, which means that in this case I'm going to have a type of resonance when I have the empty orbital plus a pi bond. So what I'm going to do, I will take the electrons of my pi bond and move them towards my carbocation. That will give me a structure where now I have a double bond on the right side and carbocation in the middle. However, I have two double bonds, and I still have a situation where my double bond is right next to a carbocation. So in this case, I can come up with a new resonance structure where I take the electrons from my pi bond on the left side and I push them towards the carbocation. Here, I'm going to end up with a structure now when my double bonds essentially shifted all the way to the right in my molecule and the carbocation is on the left side of my molecule. And with these three resonance contributors, I will mark them as contributor number 1, contributor number 2, and contributor number 3. Sometimes we're going to have the follow-up question, which of those contributors might be the major contributor. The thing is, not all of the contributors are the same. Some of them are more stable than the other ones, as if they were different molecules, but of course they represent the same species. So when it comes to carbocationic contributors, we are going to look at the position of our charge at the position of our plus and decide whether that is going to be more or less stable. The nature of carbocation is so that the carbocation is a trigonal planar species with an empty orbital around it. So we're going to have one group, we're going to have the second group, and we're going to have the third group next to it. And the more stuff we have around this positively charged empty space, the more stable our carbocation is going to be. So, when it comes to the stability of carbocations, the tertiary carbocation and the tertiary contributor, because of that, is going to be more stable than the secondary contributor, which is going to be more stable than the primary contributor. And in order to determine what type of a contributor you have in front of yourself, whether it's primary, secondary, or tertiary, just look at how many other carbons are connected to your carbon with a plus. In the case of a tertiary contributor, you're going to have 3 other carbons. For the secondary contributor, you're going to have 2 other carbons, and primary contributor will only be connected to 1 other carbon. So if we classify our 3 contributors here as primary, secondary, or tertiary, we're going to see that the contributor number 1, that carbocation is connected to 2 other carbons, so that is going to be a secondary contributor. The middle one is also connected to only 2 other carbons, so that is a secondary contributor as well. However, my contributor number 3, the last one, that one is connected to 1, 2, 3 other carbons, so that is going to be a tertiary contributor. And as we have just discussed, tertiary contributors are significantly more favorable because the carbocation is surrounded by a lot of stuff here, so that is going to be our major contributor. In the next example, I have a situation where I have my carbocation. So I have the empty orbital, I have a pi bond, and I also have a heteroatom here, I have oxygen. So maybe it will be useful for me, maybe it will not, I don't know yet, I'll have to see that. So again, since I have a carbocation next to a pi bond, my first instinct here is going to be to take the electrons of the pi bond and move them towards my carbocation. In this case, what I'm going to end up with is the double bond on the right side and carbocation in the middle of the molecule like that. Now, I reminded you before that bond line structures can be treacherous, and that is one of those cases where I do have a heteroatom, I do have oxygen here, but I did not show any electron pairs on that. Now I will do that, and I can see that now I have a situation where I have a positive charge, I have the carbocation right next to the oxygen which has an electron pair. So that is the case of the resonance when I have the empty orbital right next to the electron pair, which means that I can do the resonance one more time. I will take the electrons from the oxygen and push them towards my carbocation. What that will do, that will give me a situation in which oxygen will be now double bonded to a carbon. I have another double bond, and because oxygen only has one more electron pair left, I'm going to have a formal charge plus on the oxygen as such. Now, the same question as before, which of 3 of my resonance contributors is going to be the major contributor? Is it going to be the number 1, number 2, number 3. And probably your first instinct is going to go away from the one where we have plus on the oxygen, because oxygen is the electronegative element and we generally do not want to see the plus charges on electronegative elements. However, I want to stop you right here and let's look carefully at all atoms with our positive charge first before we draw any conclusions. In the first case, over here, I have a carbocation. We know that carbocations, they are 6 electron species, so overall I have an open shell around that. That is a 6 electron species, which is not necessarily particularly stable. In the second case, where I have my next carbocation contributor, that one is a 6 electron species as well. However, in my last case, where I have the oxygen over here, if I count all the electrons around this oxygen, I will actually have the 8 electron species, which means that my last contributor shows me the positive charge on the element with the full octet, while the other two, they have an open shell. And despite the charges, the full octet will always trample the open shell. So whenever you have a situation where you are deciding what is the major contributor and you have contributors with the open shell versus the full octet, the contributors with the full octet atoms are always going to be your major contributors, which means that in this case, that is going to be our contributor number 3. And let's look finally at one more example. In this case, I have a negative charge on the carbon, so it is the carbon with an electron pair, and right next to that carbon I have a pi bond, carbon-oxygen pi bond. So what I can do, I can take the electrons from my carbon, push them towards the pi bond. Now the middle carbon that I have right over here, this carbon has a full octet around it, so it will not be able to accept any more electrons without pushing the electrons away, so we are going to push those electrons towards oxygen. What that will give me is a new resonance structure, where I have oxygen and double bond between carbons. I remember that initially my oxygen had 2 electron pairs on that to begin with, so now in addition to those 2 electron pairs, I have the third electron pair, which used to be my pi bond, and because of that I'm going to have a negative charge associated with oxygen now. Well, in this case, if we try to do the analysis and figure out what is our major contributor, and we analyze structure number 1 and structure number 2, then we are going to have a very interesting situation. From the perspective of the electrons around my atoms, the carbon over here has a full octet because I have the 2 bonds, then I have the electron pair, and I also have the implicit hydrogen over here, so that has a full octet. Likewise, if I'm going to look at my oxygen in my second contributor, it has 1 bond, 3 electron pairs around it, so it has a full octet as well. So in this case, the deciding factor is going to be the electronegativity of the element with a negative charge, which means that oxygen, having a higher electronegativity, going to be able to stabilize the negative charge better, making my molecule number 2, or I should rather say my contributor number 2, into the major resonance contributor. So remember, whenever you are evaluating your resonance contributors, the first thing that you want to do is to check for full octets. Structure with full octets around the charged atoms is going to be the major contributor, as opposed to any structure with open shell with 6 electrons or less. If you only have carbocations or only positively charged species without a full octet, then look at the position of the plus charge. If your plus charge is on the tertiary atom, is going to be a more major contributor than a secondary, which is going to be better than primary. Lastly, if you have negative charges, you want to look at where your negative charge is located, and you want to place your negative charge on more electronegative elements. So it is better to have a negative charge on the oxygen than on the nitrogen than on carbon. Let me know in the comments below if you want me to record another tutorial where I go through a whole bunch of resonance problems and determine the major and minor contributors and go over all of those rules one more time. Have any suggestions and questions that you have for me in the comments below, and I will see you in the next video.